Part A. B and C are compounds of two different transition elements. A student carries out test tube reactions on aqueous solutions of B and C. The observations of the student's tests are shown below. Analyse the results to identify B to H and construct ionic equations for the formation of products D to H. So let's start with looking at B. So B is FeSO4 or iron sulfate. And that's because if we look at test 1, we've got a green precipitate called D. And that's when you add ammonia dropwise. So doing this and getting a green precipitate, that is a test for iron 2+. So we can write that test 1 is showing that iron 2+ ions are present. Then if we look at test 2, we have a white precipitate G. So this white precipitate, when we're reacting nitric acid followed by barium nitrate, that's a test for the sulfate ions that we have in B. So we can say that test 2 shows that SO4 2- ions are present. Then we can start thinking about what precipitate D and G are. So if we do D first, D is equal to FeOH2 or iron hydroxide, and G is equal to barium sulfate. So D is because we're adding this base, we're adding OH- to iron 2+, so we get the compound D as a precipitate. And then G is because we've got this sulfate ion, it likes to be with barium, so it's going to displace this nitrate ion. So this we've looked at B because we've got no change with test 3. Now if we look at C, so C is equal to chromium chlorine 3 or chromium chloride. So the way we can work this out is if we look at test 1, we have a grey-green precipitate E and then a purple solution F. So these colour changes when you react with a little bit of ammonia and then a lot of ammonia. So that is a test for chromium 3+ ions. So they're present because we've got positive test. And then if we look at test 3, because test 2 has no change, in test 3 we have a white precipitate H. And that's when we are adding this silver nitrate to nitric acid. We're getting this white precipitate. And that's a test for a halogen. And because we've got a white precipitate, we know it's going to be chlorine or a chloride ion that's present. So that's how we can work out what C is. Then we need to look at E, F, and H. So looking at E first, similar to looking at B, we have CrOH3. So rather than 2 in ion, because in iron we've got this 2+ charge, so we need 2 OH minuses. In chromium we have this 3+ charge, so we need 3 OH minuses to balance this. Then if we look at F, that's going to be square brackets CrNH3, and we need 6 of these, and then we're going to get a 3+ charge. And that's because we've got this excess of ammonia, so it's present in our complex. And then finally, H, we have silver chloride. So that's a common test for halogens. Now we need to construct these ionic equations. So if we start looking at D, so that's going to be iron 2+ plus OH- going to FeOH2. So we need 2 OH minuses. So, and then if we go on to E, it's a pretty similar equation where we have Cr3+ plus 3 OH-, and that produces CrOH3. So these are our two hydroxides, and they're very similar ionic equations. Finally, if we look at F, so we're starting with our product from the last step. So we're starting with E, and then we're adding more ammonia. So starting with E, we start with CrOH3. Then we're going to add ammonia because we're adding excess ammonia. And then we're going to produce this complex of CrNH3 6 3 plus 3OH minus, because this ligand has been substituted for the NH3 or ammonia ligand. Then if we look at G, that's going to be Ba2 plus SO4 2 minus, and then that's going to produce BaSO4. So here the arrow's slightly slanted, but it's producing barium sulfate. And that's because we've got this 2+ charge present in the barium nitrate, and then you're replacing the nitrate ion with the sulfate ion. And finally, if we look at the formation of H, so that's going to be a silver ion plus a chloride ion, producing silver chloride of AgCl. So to get the 6 marks for this question, it's a level response question, which means there aren't specific marking points. Instead, you must have all 3 tests covered in detail, with at least 6 of B to H identified correctly, and the equations must be mostly correct. You must also have a well-defined line of reasoning which is clear and logically structured, which we have in this question, with showing what's present in each test. We have the ionic equations for all of the relevant reactions, and then we've correctly identified B to G. Part B. A compound of nickel J has the formula NH4(2)NiSCNX(NH3Y) and contains SCN- and NH3 ligands. The percentage by mass of 3 of the elements in compound J is shown below. Ni is 16.26%, S is 35.56%, N is 31.00%. Part 1. Calculate the values of X and Y in the formula of compound J. Let's start by highlighting the key pieces of information in this question. So that would be the formula of J and the percentage by masses of the 3 elements, and that we need to find the values of X and Y. So looking at the percentage by masses, we can work out the ratio of nickel to sulfur to nitrogen. So what we need to do is 16.26, so the percentage, divided by the relative atomic mass, which would be 58.7 for nickel. Then we do the same for sulfur, so that's 35.56 divided by 32.1 for sulfur. And then for nitrogen, we have 31.00 divided by 14. So this equals 0.277 to 1.1 to 2.21. So then we divide by the smallest, so 0.277 divide by 0.277 and divide by 0.277. So this equals 1 to 4 to 8 as the ratio of nickel to sulfur to nitrogen. So then we know that X is going to be equal to 4, because the only place we have sulfur is where X is, and there are 4 sulfurs, so X must be 4. But then for Y, we know that we've got 2 nitrogens in this NH2 here, or NH4 brackets 2. So there's 2 nitrogens here. There's however much X's nitrogens, and then you've got Y here. So, and all of these added together will equal 8. So 2 plus X plus Y is equal to 8. Well, we know that X is 4, so that's going to be 2 plus 4 plus Y is equal to 8. So Y must be 2. because 2 plus 4 is 6 and 8 minus 6 is 2. To get the 3 marks for this question, you get a mark for your ratio, so 1 to 4 to 8. Then you get a mark for X and a mark for Y. Part 2. Determine the oxidation number of nickel in compound J. So for this question, we're looking at the formula and trying to work out the oxidation number of compound J. So this could also be known as the charge of nickel in compound J. So we know that the only ligand with a charge is this SCN-, and we know that X is 4 from the previous question. So we have a 4- charge for all of our ligands because ammonia, or NH3, has a 0 charge. Then we need to look at this NH4. So this is what most people don't look at. This will have a charge of +1, and there are 2 of them, so that's +2. So if we did -4 and then +2, that's going to be -2, but we want a 0 overall charge. So that means that the oxidation number of nickel must be +2 in order to make this 0, because -2 + 2 is equal to 0. And to get the mark for this question, you must write +2. Part C. Sodium sulfite 4, Na2SO3, is used as a preservative in some foods. Food safety legislation allows a maximum of 850 milligrams of Na2SO3 per kilogram of burger meat. A chemist determines the amount of Na2SO3 in a sample of burger meat using a manganate 7 titration. Step 1. The Na2SO3 from 525 grams of burger meat is extracted to form a solution containing SO3 2- aqueous ions. Step 2. The solution from step 1 is made up to 250 centimeters cubed in a volumetric flask with water. 25 centimeters cubed of this diluted solution is pipetted into a conical flask. Step 3. The pipetted solution from step 2 is acidified with dilute sulfuric acid and then titrated with 0.01 moles per decimeter cubed potassium manganate 7, KMnO4. 12.60 centimeters cubed of KMnO4 aqueous is required to reach the end point. Analyze the results to determine whether the burger meat complies with food safety legislation. Firstly, with this question, let's highlight the key pieces of information. So that's going to be the mass of burger meat we're using, the volumes in the titration, so the scale factor of 10, the concentration of potassium manganate, or KMnO4, the volume required to reach the end point, and then we're going to start using some equations. So the first equation we're going to use is an equation triangle of the number of moles is equal to the volume times concentration. So we can work out the moles of the manganate ions. So we can do 0.01, which is its concentration, multiplied by 12.6 times 10 to the -3, because we're converting centimeters cubed into decimeters cubed. And that equals 1.26 times 10 to the -4 moles of MnO4-. Then if we look at the scale factor of the manganate and the sulfate ions, we have a 2:5 ratio. So to get the moles of sulfate ions, we need to do 1.26 times 10 to the -4, then divide by 2 and times by 5, which equals 3.15 times 10 to the -4 moles of the sulfate ions, so SO3 2- in 25 centimeters cubed. This is very important because we need to use the scale factor of 10 to get to 250 centimeters cubed. So we do 3.15 times 10 to the -4 multiplied by 10, and we get 3.15 times 10 to the -3 moles of SO3 2 minus in 250 centimetres cubed. So now we've effectively used the molar ratio and the scale factor to get the moles of the sulfate ions. Now we're going to use a second equation triangle to help us work out mass. So mass is equal to moles times relative formula mass. So we've already got the moles, which is 3.15 times 10 to the negative 3. And then we want to multiply by the relative formula mass of this sodium sulfite, so Na2SO3. So that's going to be 23 times 2, which is the relative atomic mass of sodium, then plus 32.1, which is the relative atomic mass of sulfur, plus 3 times 16, which is the relative atomic mass of oxygen. And then if we do this, we get 0.397 grams of sodium sulfate, so Na2SO3, in 525 grams of meat. But we want it per kilogram, which is right at the beginning of the question. So if we're trying to convert this into per kilogram, we need to do 0.397 multiplied by 1,000 divided by 525 grams. So 1,000 grams is in a kilogram and we're dividing by our number of grams. So this equals 0.756.6 grams, which if we convert to milligrams is 756.6 milligrams. Then we need to look at what we're allowed. So we're allowed 850 milligrams. So 756.6 milligrams is less than 850 milligrams, and therefore our burger meat is complying with these food safety legislation and it's safe to eat from what they've told us. To get the 5 marks for this question, you get a mark for working out the moles of the manganate ions. You get a mark for working out the moles of the sulfate ions. You get a mark for working out how much is in 250 centimetres cubed. Then you get a mark for working out the mass of sodium sulfite in 525 grams. And then you get a mark for working out how much is in a kilogram, and then saying at the end that it's less than 850 milligrams.